Hello everyone. In this video, we can see how we can stimulate a third order width extraction mode in a piezoelectric material using COMSOL. The resonance frequency of third order width extraction mode is given by the formula F is equal to 3 by 2W root of E by rho, where W is the width of the material, E is the Young's modulus of the material, and rho is the density of the material. So if you have this is for one of if you have only one layer of material. So if you have a stack of material like two layers, three layers, etc. So then the formula changes. So for that, so if we have two layers, then E the effective Young's modulus is given by the formula E1 T1 plus E2 T2 divided by T1 plus T2, where E1 is the Young's modulus of the first layer, E2 is the Young's modulus of the second layer, T1 and T2 are the thickness of those layers. So similarly, you can find the effective density also. So there you will, so effective density rho is equal to rho 1 T1 plus rho 2 T2 divided by T1 plus T2. So once you have the effective density and effective Young's modulus of the stack, you can find the resonance frequency using this formula. So in this video, we're going to take the example of a zinc oxide over a silicon substrate. So a Young's modulus of zinc oxide is 140 gigapascal. Similarly, by Young's modulus of silicon is 168, like and density. So once you have all these values and also the width for a particular width, you can actually calculate the what is the resonance frequency uh, of your stack and of your device. Then I have calculated using these values, and I've got like for third order the value is 31.2. So for first order audio you can just divide by 3, so that is 10.4. So now we can simulate this device in COMSOL. In COMSOL, first we have to select the model wizard. So since we are making a 3D structure and doing it, we are going to select 3D, and here we select structural mechanics and then click done. So now since our material dimension is in since our device dimension is in micrometer, we can select micrometer, and we are going to start making the device. So first we have to make the silicon substrate, right? So for that I'm just selecting the first block. For that I'm giving a width of 1000, depth of 400, which this is actual width which we are considering. So there's this is how it is labeled in COMSOL. Usually we consider like we call it like length, width and height, right? But here they give width, depth and height. So it's just convention, so we need to just understand that our depth means the width, which is 400 micron, which we have taken before for calculation. So for height of the silicon substrate I'm giving 30 micron, and then we are going to make the next block, which is our piezo material, which is zinc oxide. So the same, also the length is same, width is also same, height is I'm giving 1 micron. So here we need to know that this is on top, right? So top of the SA substrate. So SA substrate thickness is 30. So I need to give Z of 30 so that it comes above the uh, first block. Now I need to give two anchors to this uh, device. Like you can also do with extension mode without anchors also, but actual device will have anchors on both sides, right? So for that we are giving anchors. So for that I'm giving another block with this 50 I'm giving, and depth of 10 and height of 30. Why we are doing 30? Because we have given the silicon substrate height as also 30. So we need to attach that on the silicon substrate, our anchor. And what is the x value? X should be minus 50, right? Like since our width is 50, it should be coming minus 50, starting minus 50 in the x direction. Then if we are trying to put at the center, so Z will be how much is the depth? It is 10. So Z should come at minus 195, right? Because since the width is 400 of the whole structure, the center is 200. So you can understand from that. So x is minus 50, y is 195, and z is 0. And we're going to make the next block. On the other side, we need an anchor on this side also. We made one anchor here. We need one anchor on the other side also. For that, width is 50. Uh, it's the same thing. Depth is 10 and height is 30. Here also, it should be x is 1000, right? So you can see from here till here is 1000, right? So x should start from here like that. So y is 195 and like that. So we have made build all of this. We have made our base. So now we need to give the material. So I right click on the material. I choose what all materials I have. One zinc oxide and one silicon substrate, right? So I choose semiconductor. In that silicon I choose, which is the silicon crystal anisotropic. That is what I'm choosing. So I have chosen one material. Then I need to choose one material, right? For our zinc oxide, it's a piece of material. So I'm adding the material. Piezoelectric I choose in the piezoelectric section. I'm going to choose zinc oxide. Yeah. So now here I have to select zinc oxide. It's a top layer. So other silicon is all my anchor uh, and the bottom substrate is silicon. So that is done. Now after that we need to add another physics also. So you can also add from here also, since I already have done this before, it is coming here. So here I am adding solid mechanics. So I should think what all things I should do. My boundary condition is such that I need to fix the angles, right? So for that I am going to select that fixed constraint. So where all I need to fix? One is here this side, next is this side. Zooming in so that I don't make any mistake. Yeah, fine. So I have, and that now what I should do now, I should give so since this we have a piece of material, we need to put a material model piece of material also. So it is taking some time to come. Yeah, piece of material I am giving top layer is piece of material, that is our zinc oxide, right? So I have chosen that. And so here our silicon is anisotropic, right? So for that I need to change the solid model from isotropic to anisotropic. And once that is done, then now I have to give the voltage, right? Then only it will be, you can get it to a with extraction mode, right? So for that I need to give voltage. For that I need to, I'm selecting electrostatics. So here under electrostatics I need to select terminal. So in terminal, yeah, so I am giving top. There I am giving, so I need to, I am giving voltage there. So it already came 1 volt, so we can try with 1 volt. So I also need to give ground. For that I am selecting ground. There I need to give ground at the bottom of the piece of material. So I'm just zooming in so that I can correctly give it that boundary. Yeah. So the bottom of the piece of material I have given the ground also. Now that is also done. In multi-physics, I need to select piezoelectric effect because I am doing a piezoelectric study, right? So because then only it will take the conversion from electrical to mechanical and like based on that, so many things are there. So it considers a lot of those things. So for that, you need to choose my piezoelectric effect one. Now that is also done. So we need to check whether everything is fine. Yeah, here silicon it is showing into mark. So we need to see what is that. So here you can see relative permittivity is not given. So here you will give 11.68, which is the relative permittivity of silicon. So that is given. Now we need to uh, add our study, which is our eigenfrequency study. So for that, I'm selecting here eigenfrequency in the study section. So other two we selected was from physics section. Now we need to select from study section, like here. So this is sidely it is already there. Satisfied. I can easily take it. So select eigenfrequency. And there it is asking decide number of frequency. How many frequency do you want to scan around? So I'm giving a rough of 50. And give how much you want. So we have calculated already that the first order mode comes around 10.4, right? We can see where the first order width extension comes around 10.4. It won't be exactly 10.4, but that is what we calculated, right? So you can see, so that will give us an idea where to expect the resonant frequency, our calculation. So now we can compute and see. So it is number of degrees of freedom solved for is 96700. So you can see. So I see you can see I have not added a mesh, but still it is showing. So it usually sometimes it takes a normal mesh. So yeah. So we are expecting around 10.4, right? Let's see where we are getting our resonance, our width extension mode. So for this thing, we can also change the color. So here I am going to select a rainbow color, which will give us a better like better contrast, I feel. So I selected that. Now you can see more shape. Here alone we have not got any width extension till now. Yeah, so you can see. So how would I find it? So you can see center line which is completely blue, right? That means it has almost least displacement. That is a node point. So when you have a least displacement point like then you can understand that it is a width extension or length extension. You have it in this part. So you can see the animation by clicking here and play. So we have got the first order width extension at what frequency? We have got at 9.56656. So we can expect the third order width extension around 9.56 into 3, that is 28.68. So we can simulate around that frequency and compute around that frequency and see whether we are getting some 28 I'm giving. And around that we can compute and see. So it'll almost take the same time. Last time you can see it took like 29 seconds for it to come forward. So yeah, this time it came a little more fast, like 24 seconds. So now we can see we expect around 28.68. So it should be somewhere near that. We should have that third order with extension mode. Yeah, 28.53. So how I know it with extension, because you can see width is like coming inside, and also you can see the center node and two other nodes here also. So from that, so you can see in the animation that it is a width extension mode. So we have got our width extension around 28.537 megahertz. So so this is how you can simulate a width extension mode. uh, so I hope you like the video. If you like the video, please subscribe. So thank you.